Howdy, everybody. Welcome to day 21 for Advent of Code. We're just getting we're just getting towards the end here, I guess I should say. There's still a few days left, though, and I don't know about you, but this problem was kind of a beast for me. So it might be coming out late. I guess I don't know when you watch these videos, but this one took me quite a while to figure out. My wife probably is wondering where I've been all day, especially since I took the day off work. Yeah, if I was working, I probably wouldn't have finished this one today. So anyway, let's just get right into it and see what everything looks like. So for this one, it's called step counter, and that will become painfully obvious why in a second, especially when you get to part two. But the idea is you fix the problems, and now all the machines are working and they're sending sand to Desert Island. I think that's where you're at. I do read the stories, by the way. It's fun to read and understand what's going on, but I figure I won't get too far into the details with you here because we're really just doing an analysis of the problem. But the story does entertain me, so excuse me. So where you land, you're by an elf who is in a garden, and he wants to do some walking. And notably, so again, you're going to be given a grid, and you're going to be given a position of where he starts in that grid. I think I called it garden this time because he said he's in the garden and he want to take some steps. And he says he wants to take exactly 64 steps. And the question that's being asked is, given this start position, like, again, this is the test, it's not the real input. The real input is much larger. What open positions could he get to if he went exactly 64 steps, right? So not up to 64, but exactly 64. He can't go in these hash marks. These are rocks again. So another grid with rocks and open spaces. So the way to think about it is, as he's moving, like, let's just say he can only move in the first, he's only taking exactly one step. Well, right here, you can only move up, down, left, or right. So the only places he can go are right here and right here, right? Now, if you ask yourself the question, well, what if he could only move in two positions? Well, the naive approach that I initially implemented was, well, start here, and then from each of those positions, where could he go from there? And so from this one, he could go up, and from this one, he could go here and here. And in this time, there was no issue with backtracking. So when you go to step 3, and so this is step 1, this is step 2, at least down this path. For step 3, you can actually go back, right? But you could also go here and here. Oh, I should mention that for this step here and this step here, when I said you can only go this way, that's not true, because you can go back to the start position, right? So if you're right here and you have one step left, you can go back to the start and back to here. And so that's what the test input kind of describes, right? So if you start right here and you go one step, these will be the places that you could have gone. If you go 2 steps, it's now going to be, think about each of these positions, which directions could I go, here or here? For that one, for this one, I can go here, here, or here, right? And so that means what it looks like then is this. And then a 3rd step, now you've got it even more, right? And then it kind of gives you a 6th step which is even farther. But hopefully you get the gist of what you're trying to do. Is you're slow. If you think about what's going to happen, is you're going to take a step, and then you're going to expand the number of steps you take, or you're going to look at all the directions you can take, and, like, I don't know, split yourself in half or in quarters and go to all those other steps. And then you're going to split yourself for each of those and go to all those places. And then any of them that you hit, or any of those that you end up in after 64 for the final solution is where you end up. So when I started doing this, my initial thought was, okay, so the naive approach would just be to, like, move, check all spaces, move, check all spaces, move, check all spaces, until you get to the 64th one. And that will work for small steps, but it won't work for large steps. Why? If you think about it, each time you're checking a position, you're checking 4 new positions, 4 new steps as you're going out, right? So right here, there's a potential to go 1, 2, 3, 4 places, right? Obviously you can't here, but you can imagine there's a potential for you to expand that much, right? So the input size was something on the order of like 4 to the 64, right? If you were doing the very naive approach, it would be 4 to the 64. But I did want to implement the naive because I thought maybe it would give me some like insight into the problem. And so let's just start with that and look at that code, right? Obviously we want a point, right? We're going to track all these positions on the grid. So having some point structure, because we'll be able to go up, down, left, right, I implemented an add function to do that, right? So, or I implemented add so we could add points. And then I also had this calculate neighbors function, right? So basically just given my current position, my current point, where can I go up, down, left, and right? And that's what these 4 produce. We'll shrink them later. But then the next step is now I need to like know about the garden and the information in it. So what do I need to know? What am I tracking? The rocks, right? Obviously I need to know where the rocks are, because if I obviously can't go to where a rock is. I need to know where I start, right? So they give you the quote unquote the start position where the elf is right now. And then these min X and Y's were just for tracking purposes. I use them because in a lot of the logic, especially when I was testing part 2, I was like expanding the grid, and my min X's and Y's were no longer 0, and my max X's and Y's were no longer like the length of the grid, right? I now expanded them out, and so my min X's were now some like multiple large negative number, and so that's just me tracking those. So how do I parse the input given the string? Well, I want to know my max X and Y, and so that's just the count of the lines and the count of each character in the line. And I could have used an iterator to go through and find the rocks in the start position, but it felt easier just to do a single, this little thing right here, and then just update the start position in the rocks as I went in. There's potentially a way to do it. I originally did it as 2 iterators, one to find the start point and one to find each of the rocks, and collect those into a hash set. I am using a hash set, right? Because I'm only interested in the points where the rocks are, and I'm really just going to say, like, is there a rock here? And if there is, I don't want to do it, right? So, but I just did it in 2 for loops, and I just said, hey, if it's an S, I'm going to set the start to that position. If the character is a rock, then I want to insert that into my rocks. So given that, there's not much to it, right? Now I have a garden, which has a list of rocks and the start point, and then my min X and Y values, so I can like find my positions. Now that I think about it, I probably could have implemented those as points. I don't know why I didn't. I could have had a point for the min and the point for the max, because it is a square. The other thing I did is I knew I wanted to do some analysis, so I created a little print function so I could simply print it out and look at it. And we'll actually show those in a second so you can see, right? Basically, I'm just looping through all of the points from the min to the max. And if it's a hash, it's a rock, I'm going to print it out. Or if that position is in the rocks, I'm going to print out this. If it's in the points that I've found, which is this thing right here, initially that's empty, but when I do the naive thing, I'll have some positions that I found. I'm going to put that as an O. If it's the start, I'll put it as an S. Otherwise, I'll print a dot for it, right? So this is just a simple helper function for me to visualize. I also have this neighbors function that I use for multiple algorithms. And this one's pretty simple, right? Is given a point, I can get all of its neighbors, which is every direction now, right? And then I just have to, if I want to know what the actual neighbors are, I just have to filter by like these values, right? These four are just making sure I'm on the grid. And then this one is just checking to make sure it's not a rock, right? So my neighbors will start at 4, and then this will reduce it down, to up to 0, right? Depending on where, what it looks like from the neighbor's position. It won't ever be 0. There is a weird case if you're trying to find like positions. Like initially, later I implement dijkstra to try and figure this out. And there are positions that aren't rocks, but they're surrounded by rocks. And so if you're going some other approach, you might run into that issue. But for here, that it didn't really matter. So I could just, say, hey, if it's not a rock and it's not on, it wouldn't take me off the edge, then I can use this. There'd be no place, I guess, where my point was this neighbors function would actually probably never return 0 unless you were doing 0 points, unless you were doing dijkstras. So sorry for that little sidetrack. But again, my neighbors function is just taking my 4 points and filtering it down to actual valid neighbors. So maybe a better term would have been like valid neighbors for a given point. Okay. So what does the naive approach look like? Well, I'm going to pass it a number of steps. And the reason I do that is because when I was testing at the beginning, I kind of wanted to know how many steps it took, or like what it looked like at 1 step versus 2 steps versus 3 steps. And I used a helper function here. You could have potentially done this in some kind of loop. And you'll see later I did do like an alternating one as a loop. Either way, I need to track the points that I found, like the positions, and from my start position, right? So, what does that helper function do? Well, again, I said it's recursive, so I need to have some kind of sentinel check, and that's this right here. It's me saying, hey, if my step counter is ever 0, I know I can't add anything to the point set, so I'm done. Otherwise, I'm just going to iterate over all the neighbors, and I'm going to recursively call this naive helper function on all of the neighbors with a step to -1. So you can think about this as like every time I find a point, I'm going to look at all the neighbors, and I'm going to call this same function on all of the valid neighbors. But when I get there, I will have taken a step, so I should decrement my step. Right? So you imagine, again, you're like right here, and you take a step right here. Now you're 1 step less to your goal, but you have new points that you want to investigate. And so when do I add my points? At first, I actually struggled with this because I was just always adding points. But the realization is that you only actually add the points if your step counter is 1, right? If you only have 1 step left. Then this point is interesting and it should be included in that thing. Again, this is the naive solution and it's really slow, but it's what got me to seeing the grid, right? And if you think about it, is you've kind of like fanned your way out and in all directions to all the possible positions that you could have stepped. And once you get to that final step where your steps is 1, you can insert it. Then at that point is where you want to insert it, right? And so this is kind of like I don't know, you could think of it as like a depth first search, as you're kind of scouring out through the thing and finding the end steps and then marking those as points that you would hit, and then roll your way up to get to the final solution. So this was my naive solution. It's not a great solution. Again, it doesn't work. But what did it get me? It got me this. And I knew I couldn't do 4 to the 64 checks. So I wanted to kind of start looking for what was going on. And you can actually almost see it in this. It's hard to show, but like, notice that when you step here for this one, if you go to the one after it, those points are also there. There's just more additional points as well, right? And so that's what kind of led me to like, oh, is there some kind of like pattern that's going on? And you can kind of see there is, right? Is like any of the odd times, any of the odd steps are equal to the previous odd step plus the points on the even step, or I should say, plus the valid neighbors of the even steps, right? So it's going to be these, and then these are going to produce some even ones around here. But you can see it, even as it gets bigger, like this is a subset of this one right here, right? Maybe I show my little thing right here. So like these two right here are in here, in here. So any like previous odd position is going to be a subset of the other position. And that was a good way to think about it for me, is I was like, oh, clearly there's like some, because you're stepping, there's this like very notion. So if you're going 64 steps, you know that it's going to be all of these even ones that are going to account for it, right? And so even though the naive point didn't get me there immediately, right? This is only 10. I'm only going 10 steps, right? So here's the starting node, and then here's a 10 total of steps. I was able to get this in just some number of milliseconds. But once you start getting higher, right? 4 to the 10 is not super big, but 4 to the 64 is extremely big, right? It's like, I don't know, some ginormous number that I can't even think about. So you can't take this naive approach. So I actually had a couple ways that I thought about it. My first way was, can I just do these odd evens? And my end-all solution actually ended up being similar to that, right? My thinking was, what if I just track the odds and track the evens, and then I know I only need to, like, if I'm on an even step, so say I'm in this position right here. Well, let's do it this way. Say I'm in this, I'm right here. I know that like this next one is going to be like this one, the neighbors of this one that are valid, unioned with the neighbors of this one that are valid. If that makes sense. I hope that makes sense. It didn't work very well though, and the reason was it was hard to like it at least I think I may have had a bug in it, because the idea of that I think is actually correct, right? Is like, if you find all the neighbors of this one and union it with this one, you will always get that one. And so I don't actually know why it didn't work, but I couldn't get it working, and so I tried some other paths. One path that I actually tried, I have my notes in here of different things that I tried for all the different parts. When that didn't work, I actually moved to dijkstra, right? So I went through the entire grid, and anyone that wasn't a rock, I calculated the shortest path to it, right? So this one, I don't know exactly what the shortest path would be, but it'd probably be something like this. So this would give you a value of, say, 12 or whatever, right? And so I calculated all of the shortest paths, and that actually gave me the right answer, right? So once you calculate the shortest paths, you just need to know, is that shortest path odd or even? And is it less than, or sorry, you actually don't need to know if it's odd or even. You just need to know if it's less than the number of steps, right? Because the question is, could you get there in that number, in that less than that number of steps, I guess is the way to say it. So, and that actually got me the right answer. So I solved part 1 using Dijkstra's algorithm, which we had done a couple days before. So I won't talk too much about Dijkstra, but that actually gave me the solution to part 1. It did, for the input, it took like 10 seconds, because the input grid is 131 by 131. So I had to calculate Dijkstra's algorithm on, I don't know, whatever that is, like a 100,000, a couple 100,000 of these points, and then go through some stuff. And so it didn't work. So I shouldn't say it didn't work. Once I got to part 2, I realized that, oh, there's no way I'm going to be able to solve this using Dijkstra's algorithm, and we'll talk about that in a second. So I did go back to the odd even thing, and the way that I changed my mind about it was, remember how I was originally thinking like the way to calculate this is just the union of this plus the neighbors of this. Instead, what I thought was, as you're going, instead of like going very deep, it's almost like I don't know, it's not really dynamic programming, but the way to think, sometimes in dynamic programming, you're really just interested in like, hey, what is the result of my previous neighbor or whatever would be the way to describe it. And so, okay, so the way to think about it, the way that I thought about it was, I'm still interested in this odd even, but instead of it being odd even, I'm actually interested in like my current set and my previous set, right? And the way to think about it is, given any one of these boxes, I can calculate the next box. So this would be, if I want to calculate this box, this would be my previous box. I would just go through all the O positions and find their neighbors, right? Find all the neighbors and fill them out. And that would be this next box. Now, if I want to fill this box out, this is my previous box, and I'll find all the neighbors on this box, and then this will become my current box, or current garden, I should say. I said box a bunch, I'm sorry. My current garden. So the way to think about this one is any garden you want to, any number of steps you want to take, you just need to know the previous steps, values, positions, and then you just find their neighbors and solve them. So how does that one look? I called it alternating because I was still kind of alternating between the two. So how does that one look? It is right here. And it turns out to be much simpler and faster. So you can see here's where I was doing my initial testing. I tried to keep this around. You can see for the test input, it solves super fast. What does the alternating look like, though? Obviously, I'm going to have a set. I need my current set, right? Here's my current list, and it's going to start with just my start position. And then I need my next list, right? What is my next one going to look like? I think I said current previous here, but I used current next. It's both the same, right? Is your current one is what you know, and your next one, in this case for this algorithm, the next one is what you'll learn, right? And so how do you do that? How do you like find the next one? Well, or how do you find the end, I should say? For each of your steps, right? You're going to iterate over your current list, find the neighbors, and insert your neighbors into the next list. And now that you have this next list, you can just swap the two, right? Now your next becomes your cur, and then you clear your next, right? So your next is now empty. I used the swap here and the clear. I think it was because the AI helped me do this, but you could potentially set your cur to next and create a new next. It is another way to do this, right? The way to think about this. The AI just found this swap and I thought it was cool, so I left it in there. But again, the idea is any previous iteration, or I can figure out my current number of steps based on the previous number of steps I had and just iterating over their neighbors and finding them. And this was much faster. And that got me to the solution to part one, right? So you can see my final part one solution. I left some of the comments in here. Here's the naive approach. And here's my alternative approach to get there. I left all this in here and I wanted to talk about it because this one actually took me some time. So don't feel bad. Maybe you got it right away and could easily recognize this cur and previous, or you found some other fun way to do it. And it happened faster than me. But this actually took me some time to analyze. So even the part one, at least for me, wasn't super easy. But I did get there with this like alternating idea approach, right? Is like, if I know my previous state, I can figure out my current state just by incrementing them. And I just keep doing that until I've gone all the way out. I don't have to do this recursive fan out approach to find the solution. I can kind of figure it out by doing it. So that's part one. And you can see I got the answer here, not too tough, but it did take me some time. Part two is much harder, right? At first, he says he's taking 64 steps. Now he's going to take this many steps. What is that? Like 26,501,365 steps. And you're like, okay, well, how can he possibly do this on this small of a grid? And they're like, well, it turns out the grid repeats infinitely. So take your grid, and if you, instead of falling off the grid, if you go too far in one direction, just stamp the grid right there, stamp a new grid right there that's identical to the original one, and you can keep going. And you can keep doing that infinitely in any direction, right? So they say, and they describe it here, if you like have this position, you can just expand it out. You still have a start in the center, but now you can just expand that grid out in any direction, right? And so then the question is, how do you get to, where does he get if he takes 26 million steps? And you can see it's some ginormous answer. Okay, my alternating approach, clearly not going to work anymore, right? This worked very well when I was just going previous to next, but it's clear now that I'm not even going to take like 1 or 2 orders of magnitude more steps, where maybe I expand the grid 3 or 4 times in each direction. I actually did that. I have an expand function, and you can look at it, right? I think it's right here when I ran it. Here's what it looks like if I call my alternating function on just the 3x3 grid. So it is small. It's very small for you to see, but you can tell it does it, but it's only doing it in a 3x3 grid now, right? And so I've only taken like I think the number of steps here I took for this problem was let me go look here. How many, here's where I expanded the grid. I took 65 times 3 plus 1 steps to get that grid, right? Clearly, I, though, can't do that a bunch of times because, you know, that's only doing like, I don't know, 200 or so odd steps. I'm still not even close to the 26 million, right? That I need, that the total 26 million that I need to take here. So I know there's got to be some other solution to it, right? But printing out the grid did help. Notice what you get when you do it like this. It is a diamond shape, right? And if you actually look at the original solution to part 1, I don't think I printed out here, do I? This is the solution for 10 steps. I don't think I print out the solution, though, for 65 steps. But what it turns out to be is it's diamonds all the way down. Is the more of these you add, the more diamonds you get, right? This is like a very like X heavy diamond or Y heavy diamond, and that's just because I have rectangles in my terminal and not squares. But it's very diamond heavy. Okay, let's zoom back into like a normal thing for you guys to look at. But you can see it's clearly a diamond, right? And so that's where I came here to step 2. Here you can actually see the diamond, right? And this is the part 1 diamond, right? So if I solve part 1 and print it out, it looks like this. And you'll notice, I don't know if I can zoom in, but it's probably hard to see, I'm sorry. At 64 steps, you're just not quite on the edge. And so that's why I did 65 times 3 plus 1. I wanted to get on the edge. And sure enough, it's all diamonds, right? As long as you're doing it this way, it's all diamonds. And it turns out as the more you're zooming out, the more you go out, you still get diamonds. And so I did this analysis and I tried it quite a bit. Even if let me go down in my notes here and just make sure I'm not missing anything. But yeah, it's a diamond shape. And I tried expanding it. Again, I did this 65 times 3 plus 1. This is the one that got me to like the full expanded of a 3x3 grid, right? So if you expand it in every direction once, this gets you the diamond. So I started looking at some numbers because I knew I couldn't just keep expanding, right? Obviously, I'm going to have to expand forever. This is only like, again, 200 and some odd steps. They want us to take this many steps, right? This is the number of steps for point 1. This is the number. That one doesn't look right for 65. Actually, it might be because they alternate. The grid size is 131. So I started doing some math. I said, well, what's the number of steps divided by 131? And it was some ugly number, this ugly number. It wasn't quite it, right? So I said, well, is the grid size a modulus of this number? And sure enough, it is. It is 65. So what that's telling you is there are like 65 there's 65 grids that you could potentially walk through to get there, right? So I played around, I did some math, and it turns out that if you the way to think about it is like if you exclude the center grid, if you subtract 1 from this and divide by the 131, you actually get 202,300. And what is that number? So, right? The way to think about that number is you are going out in each direction from the initial position 202,300 steps, right? Or 300 grids is the way to say it. So this number of steps is equivalent to walking left or walking right this many grids. And it turns out to be okay to do that. Again, I realize this is a high eye chart and hard to see. The test input doesn't do this, by the way, right? If you look at the test input, there's like blocks all over the place. But this one does not. At your starting position, you can actually always walk directly east and directly west. And you can't quite do the same for north and south, but actually, maybe you can. I don't remember if you can or not. There was like some clear... I think you can, but it just, because of the way it looks, is you kind of do it funny. Anyway, the point of me saying all this is it's clear that after doing this math, I was like, oh, okay. I now know like the grid size. It's going to be 202,000 times 2, somewhere in that order. That's going to be the grid size. Clearly, I cannot calculate that. So I need to start looking at the grids more deeply and see what's going on. And that's what I did next. And here are some examples. So I started printing out the grids. And you'll notice first that I have these odd, even values. It turns out that the grid looks slightly different if you go an odd number of steps or an even number of steps. Like if I did this +2 right here, so I went an opposite number of steps of this value, it turns out like it changes what the box looks like, I guess is the way to say it. Like imagine you're expanding all the way out and you have some full box of the grid. If you change your step just by 1, it flips that box. Whereas this box was once all odds. So if you imagine you're walking in this direction, every time you walk in this direction, it's gonna it like flips the parity of this. So, but if you walk to the edge of every single one, you always remember it's 131, so you're actually going to be alternating between like even and odd, if that makes sense. And so that's why I have the evens and odds here. The center turns out once, if you're walking all the way out to the edge, the center is always odd, and then it just alternates outward from there, right? This one's even, this one's even, this one's even, and then the diagonals match is the way to think about it. And that's because every time you're stepping, you're like alternating the even and oddness of the things, right? And so I think I do some math somewhere in here. Maybe I didn't keep it, but it might be up here in this stuff. But the idea is there's a different number of, like, in your box, there's a different number of evens and a different, it is, I put it right here, right? Right here. There are a different number of odds and evens within inside your boxes as you're going, right? So notice mine has this many and then this many for like the 3x3 grid. Those numbers alternate, right? Because they're different, I need to track the differences of when they're even and when they're odd, right? But let's think about then, knowing that I'm going to be alternating, and I've kind of drawn this grid out right here at this thing, right? This is the diamond, right? This diamond looks better because I'm using squares. But start thinking about, and what I had to do is start thinking about is, what are the total value of steps in these things, right? We know some value for the odds, and we know a different value for the evens. This one's really easy to calculate, right? We know what all the odds are within here, and so that one's easy to calculate. What we can't calculate very well, though, is like this one, right? It's like missing these edges or corners. Same thing with right here. It's missing these edges and corners. And right here, right, we want to include these steps that we took right here in the diamond formation, but we don't want to include the whole of it, right? So these are the things that I started thinking about, right? And I just want to kind of step you through the process where I was like thinking about these. So this is n equals 1. I think I call it counter or count in the actual code. Yeah, the count. This is like the count of me going this direction or that direction. So this is n equals 1, right? Because I'm only going out in one direction or I'm going out 1 in each direction. So what are these values that I want to calculate? It is obviously one whole odd. So the odds here are 1. The evens here are, if we just like ignore these little sections for a second, the evens is 4, right? And then the odds that I need to add, so think about these chunks right here. It turns out I need to add like 4 chunks, right? But if you notice the chunks I need to add like the bottom quarter of this one, or the bottom right quarter of this one, the bottom left quarter of this one, the top left of this one, and the top right of that one. Well, that ends up being like all 4 of the corners. So I'm just going to call this corners for right here, right? Or edges. I think I call them edges in the code. I need 1 total of those, right? So it's 4, but that's equal to 1 total of them. And for the evens, notice I have 1, 2, 3, 4, 5, 6, 7, 8 of them. But again, I have a whole set from here and a whole set from here, and I have a whole set from here, and I have a whole set from here. So even though it's 8, the total, the edges that I need to, this is actually the edges that I need to subtract, right? Like these are the edges that I don't want to account for my inside total. So my edge minus count is going to be 2, right? It's 2 total edges that I'm not worried about. Again, so given these 4 values, I can now figure out the total, right? So how do I figure out what the odds are and what the evens are? That's what this actual code is right here, right? So what I need to do is first calculate all of the distances in the grid. And so the way to think about that is, if I'm right here, how far is this from that, right? Oh, I'm not using my highlighter anymore. If I'm right here, how far is this position, right? It's 1. If I'm right here, how far is that position? It's 2, right? If I'm here, how far is that away from this position? It's 3, right? And so I know my 1 and 3 right here will be included in my odd set, but my 2, which is right here, will be included in my even set, right? So I just need to calculate all the distances from the start position for all of the empty grids, empty positions within the grid, and then just figure out if they're odd or even, right? And so that's what this calculate distances does. We can go to the function right now if we want to. What do? Basically, I'm just, it looks a little bit like dijkstra's, but instead of finding the start, I'm going to start at the start and kind of fan out. And instead of like finding a specific position, I'm actually going to solve every distance, right? So the original dijkstra actually did this, is it like literally picked every one. The only thing I don't need to worry about is once I've already like put a position in there, I don't need to check for a shorter one. I already know it's the shortest because I've come there from the shortest. So you can think about it as a very simplified version of dijkstra. And because, again, because instead of like calculating dijkstra at every position, I can just because I already know the previous distance, I can just add that to the current distance. So what do? I have my distances that I'm going to track. I want to eventually return those, right? It's going to give me a point and how far I am from the start position. And then I'm going to have a frontier, just like dijkstra. This is the work I'm going to do. If I have new work, I'm going to add it and process it later. So the first check I need to do is just say, hey, have I already solved this distance? If I have, I don't need to go there, right? Otherwise, I'm going to add my distance to that position, to my distances, right? So I now know that start is 0 steps away. And then I'm going to check all my neighbors and add all of my neighbors to the frontier, noting that they're now an additional distance away. They're +1 distances away. So I go through that, and so that's going to pop some new ones on there, and I'm going to process those. Have I seen it before? If so, I don't need to add it. Otherwise, I do add it. And then I check its neighbors and add those distances. And I just keep fanning that out until I've reached the end. Remember, my neighbors function up above is doing some filtering for me, right? So it's making sure I don't hit any rocks. It's making sure I don't go off the edge of the map. But after that, I'm now going to have a grid, and I'm going to know exactly how far each of these are, right? Maybe this one's 12. Maybe this one's, 3. This one's 7. I don't know the exact numbers, right? But I now know how far they are. So how do I know whether they're odd or even, or an odd or even edge? Well, remember we're stepping 65 to create the diamond. So if we are odd and we're greater than 65, we want to increment our odd counter. This is just me using a fold to calculate all these distances. This may be a little confusing, the fold sometimes. So if it doesn't make sense, essentially what I'm doing is I'm just going through each point in the grid. And if it's odd, I'm adding it to my count of odds. If the distance is odd, I'm adding it to my odds. If the distance is even to the start, I'm adding it to my evens. And then I also just need to check for the times where I want to add them to my edges, right? So if it's greater than 65, I know I'm on the edge of it. And so I just increment my odd edges if it's odd and I'm greater than 65. And my even edges if it's even and I'm greater than 65. So now the way to think about it is what this has given me is any grid like this. I'm going to draw on this for a second. I'm now going to have like a chunk like this. And I know how many of them are odd on the outside of this grid. And I know how many are odd on the inside of the grid, right? Or on the inside of the diamond, I should say. And given that now, I can, like for n equals 1, given that, I can actually calculate the distance for n equals 1, right? Let's say that the total number of odds within the grid are like 5 or whatever. The evens are 6. And then these ones are like 1 and 2. Well, I just add all these up. Well, I should say I add all these up and then subtract these to get those values, right? To get the totals, right? I know there's this many odds in here. There's this many evens in there and here and here and here. So if I just multiply the number of odds within any grid by 1 and the number of evens by 4, and then I add these corners of the odds right here, right? If I add these corners, which happens to be a whole corner, so if I add that and then subtract 2 times the evens, right? Remember, I don't want to include these. These are the corners. And I subtract that from it. I now know this grid. And that's n equals 1, right? So I have like a quote-unquote math formula for it. And I apologize, this one, again, was a little math heavy. It was a little hard for me to grok and parse, but I did eventually figure it out. And I'm not a fan of the math problems. Again, it took me most of the day to figure it out. But let's keep working, right? This is the math. This is going to explain why it works, right? So now let's look at n equals 2, right? So now I'm stepping out twice in each direction. I still want to calculate this area right here, the number of steps taken, and it still is odd, even, odd, even, odd, right? But now look at the number of evens and odds, right? The number of evens is now 4, which ironically is the same number right here. And the number of odds is now 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the number of, in this case, these have swapped now, right? If you think about it, I want to strip out these odds now right here. So the the odds that I want to subtract the corners from are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? And then the evens that I want to add the corners for are these sections right here. 1, 2, 3, 4, 5, 6, 7, 8. But again, they if you look, like these two and these two line up, and then these two and these two line up, and then these outer ones line up, and then the inner ones also line up too, right, to produce whole squares. So these are actually just divided by 4s, which is 3 and 2, right? Okay, so now I have my new evens odds and my evens corners and my odds corners, and I can do some math on n equals 2 to solve it. Okay, one more. N equals 3. Sorry, this has been long, right? It's been a lot of math, but this is what took me all day to do, and why I'm probably in the doghouse after I post this video. We're doing the same thing now, but let's do odds and evens. I had to do this 3 times to figure this out, because there was this weirdness of like, oh, why is even 4 here and 4 here, but odd is like jumping all around. The 3rd time helped me like come to that realization, right? So let's count them up. There's now 4, 8, 12, 16 evens, and there's 3, 6, 9 odds. Notice again, 9 and 9, and then we're doing some huge jumping right here, 16 and 4. And then I won't do all the calculations, but if you add now we want to add odds to it, right? We want to add these odds, and what do we want to add? 1, 2, 3, 6, 9, 12. We want to add 12 divided by 4. It is 3. And we want to subtract how many evens? 1, 2, 3, 4. 4 times 4 is 16. Divided by 4 is 4. Yeah. Okay, so right, like these are the numbers that we want. These are the corners that we want to add. But again, the same way that I talked about in the very first one, now that we know these values, we just multiply the evens or the odds by this number, the evens by this number, the odd corners by this number, and the even corners by this number. I think I call them edges because I was thinking about edges here again. So when you see in the code, they're called edges. But I just multiply that by these ones, and I've got my solution, right? Okay. So now, though, I've done 1, 2, and 3. How I now have to do it this many times, right? Do I keep going this path? Well, it turns out you can find a pattern for these. Think about what's happening here is, in the general case, can you figure out what these values are? For n equals 2, it's 4, 9. For this, it's 9, 16. For this, it's 1, 4. You start to notice a pattern, if you're not aware, of like squares and stuff like that. But clearly these have to do with like squares of n and n plus 1. Same thing right here, right? So it turns out right here, the O value is n squared, and this is n plus 1 squared. And then this value is n squared, and this value is n plus 1 squared. I didn't do that one right, sorry. This one is n squared, and this one is n plus 1 squared. Why am I'm using n here because it became a math thing for me, right? But I was doing a counter first, so I think that's why it's in the code that way. Sorry if that confuses you. Okay, what about these corner things, right? Well, it turns out that this is just n, and this is n plus 1, and this is n, and this is n plus 2, or sorry, n plus 1. This is n, and this is n plus 1. You can start to see there's a pattern, right? The pattern, though, interestingly enough, just the same way that these are alternating, is that the odds and evens are alternating as well. In the first case, the odds are n squared. In the second case, they're n plus 1 squared. And that's why you see like these, you see the values again, just in the opposites, right? You can see they're alternating. So now for this number, I only have to figure out, am I solving this one? Am I solving where even is n squared or odd is n squared plus 1? Or am I solving this one where n is odd is n squared and even is n squared plus 1? Again, it's alternating. So all of the odd ones will end up here. All of the even ones will end up here, right? So now I actually know the formulas that I want to use for this one. It's going to be n squared for even. And for odd, it's going to be n plus 1 squared. And in this case, because I'm on this thing, I'm subtracting odds. So my odd corners that I want to subtract are n plus 1. And then my even corners that I want to add are n. And there you go. That's it. Now I know if I just plug this into n in all those places, that's probably ugly, sorry, but if I plug that number into n here, I now know if I know the actual number of odds and evens in in this box, I can now plug that number in here. And so that's what the rest of the problem is, right? I've calculated my distances. I now know my odds and my evens, my odds edges and my evens edges. I have this magic number that I calculated. And then, so now I can just figure it out, right? So what are my total odds? Remember back here, it was n plus 1 squared. So it's just my number of odds times n plus 1 squared, right? My evens, it's n squared. So my total evens are n squared. My odd edges are n plus 1. So I just multiply my odd edges by n plus 1. And my even edges are just n. So it's just the number of the count, right? So now I have these 4 values. And remember here, because I'm subtracting my odds, again, why is that? There are these sections right here that I'm not interested in. So what I've actually calculated are all these boxes, right? The way to think about it, I've calculated this box like this. And what I want to, all the way up as well, I want to add, for this one, I want to subtract my odds from it. And I want to add my evens to it right here, right? So I want to add these to it and subtract these from it, and that will give me this answer. So what does that look like? The answer to P2 are my total odd plus my total even minus my odd edges plus my odd edges, and that gives you the answer to part 2. So if I run it, Hopefully I didn't mess anything up. You can see here's the answer to part 1. Again, that was my I think my alternating solution, right? And then here's the answer to part 2, some ginormous, unfathomable number, right? Remember, you're thinking about some elf walking these number of steps. I actually think, should I find it? Let me see. I asked the AI to create an image of this, right? I said, hey, create an image of an elf walking in a desert garden. This dude's walking, I don't even know what that number is. Let's see if I can pronounce a number. $600 90 billion steps. That's what this says. Sorry, I was looking on the other thing. This dude's walking 600 billion steps, right? So he's got a ways to go. But there you have it. That's the solution to day 2. So how do we close out day 2? It was a lot of math again, and I don't mind doing the math. I think problem solving is fun. Obviously, I very much like computer programming. So when it's something like, oh, can you implement Dijkstra, or can you do A star, or can you like find a dynamic programming solution to it? Dynamic programming solution to it, right? Or, oh, this is clearly a DFS or a BFS, right? Those things are really fun for me. The math ones are less fun, but I still like to solve the problems. And this was a lot of math heavy work. Again, it took me hours to get here. So I would be curious from you guys, how long did it take you to get to these positions, to get here and figure it out? Or did you find some other way? If there's an easier math way, I would love to learn how to do this. Or a programming way. I don't know how you do this programmatically. I should say again, much like yesterday, was it yesterday? This is very unique to this specific number, right? If it's almost any other number, if it's any number, especially particularly that doesn't cause the grid to like produce, how do I say this? If it's not a number that like clearly creates this diamond shape for your grid size, the input plus this number, this solution just doesn't work, right? And I think I haven't looked at the Reddit stuff, but I'm almost positive there will be people that don't like this, because in years past, people have always said, oh, I don't like these solutions where you're solving a problem that's like solely based on the input, right? I think in one of my things, for part 2, you can see I get this value. This is clearly not the right answer for part 2 for this input right here. And it's because your input, at least my input, I presume yours works similarly, your input is very geared towards coming to this epiphany, right? At least in my mind. Maybe there's some other way to do it, but it's very clear, I guess what I should say is that that the input is geared to lead you towards some kind of mathematical solution. Again, I don't have like an advanced degree in mathematics, so there could be some matrix style things that you do. I've taken linear algebra, but not any advanced stuff, right? So there could be some way for you to like solve this some other way. I just don't know what that is. And so this one was, again, very math heavy. Look at the problem, right? So I go from here to just solving like the general case, the one case to 64 steps, and realizing it's a diamond shape like this. And if I go exactly 65, it's very diamond shaped to the edges. And then if I go like this, where I've expanded the grid one time, it's still a diamond shape. And so from there, you can kind of extrapolate, oh, there's something I can do here. So can I start analyzing what this stuff looks like? And that's what got me to the solution, right? Again, very specific to the problem and the input. I don't know if there's like a generalized solution. I'd love to hear from you guys, though. If you have some generalized solution that works for any number of steps of arbitrary size, that would be really cool to see, because I didn't get there, at least for day 21. So there you go. That is day 21. Again, it was a mess and it took me a while to get here. So I hope you guys enjoyed it, though. It was fun for me. I enjoy solving these problems, I should just say again. So I don't want to like make light or bemoan like these math ones, because they can be really tricky, but they require a lot of thought. And sometimes you don't know, right? Like I think that we talked about the last time, the shoelace one, I didn't know. This one, you didn't need any advanced math, I don't think, but you did need to like draw it out and think about it, and it would get you there. So there you go. I hope you guys enjoyed the video. And we will talk to you tomorrow for day 22, assuming it's not any harder. If it is, it'll probably be the next day. So see you later.